history through the material balance spreadsheet. What I want to walk through now is a couple more examples, each of which have active aquifers in place. And so the first example that I'm going to walk through is one of an undersaturated reservoir without a gas cap, obviously, and an Edgewater drive that is supporting the pressure. So hang on and let me load up the production data for this particular example, and I can walk you through it. Okay, so here is the production history for this particular example. This example is based on one that I saw in the Dake textbook, and it shows the oil field is producing around 6,000 or 7,000 barrels a day, some fluctuations in production, in oil production as time goes on. These are 50-day time intervals from one point to the next. And you can see here that there's a period, I think it's 250 days if I'm not mistaken, of a shut-in period. And then we go back to production again. This data here is the water production data. And you can see that as time is going on, water production is rising up to around 1,000 barrels a day. Again, the field becomes shut in for a period of time, and then the water production comes back on again. And down here we have the GORs for the field, and they're very constant at 400 standard cubic feet per barrel. And the reason why they're constant is because, again, we're above the bubble point pressure. This information down here is the historical pressure data that has been captured from the field, again on a 50-day basis. And you can see initially the pressures are dropping down as depletion occurs from the production. Then during that shut-in period, it's interesting to see what happens is the pressure is actually rising. The measured pressures are rising, and that's due to a response and influx of water from the aquifer, which is causing that rise in pressure. And then once the production then starts up again, pressures continue to drop off. Okay, so we're going to analyze that data with the material balance spreadsheet. So here is the material balance tab from my spreadsheet, and I've got it set up reasonably well here in order to proceed with the analysis. First of all, I'll point out that in this case we're going to be using tabulated PVT properties, and we have them just typed in here. We've got the reservoir pressure sorted lowest to highest. We've got the formation volume factor for oil. We've got the solution GOR, a constant 400 cubic feet per barrel, and the accompanying Z factors. Okay, so because we're using the tabulated PVT properties, or in other words, a table lookup technique, this is why I have a 2 entered here rather than 1, which I would use if we were using the PVT correlations as we did in the first example. Because we have an aquifer connected to the reservoir in this example, I have selected 1 here, which means yes, that we are going to be considering water influx. Again, we're well above the bubble point pressure, so the M value is 0 in this case. There is no gas cap. Estimated water saturation, average water saturation for the oil reservoir is just under 25% porosity, and the average porosity for the for both the oil and the oil zone and the aquifer is 19% porosity. In this case, I've chosen to use a specific rock compressibility that does not come from correlations. So I've typed in yes here, and I've typed in the raw compressibility that we want to use, which in this case is 5 times 10 to the minus 6 per psi. And that forces that same number to pop up here. And this water compressibility value is being read directly from the water PVT properties tab that we see over here. Okay, so that's coming directly from those inputs. To continue on, the aquifer properties that we believe we have in place. First of all, it's an Edgewater drive, as indicated by the 1. It's the oil zone has a radius of, we believe, around 6,000 feet, and the thickness of the aquifer is approximately 150 feet thick. And the permeability is around 10 millidarcies in the aquifer, and the viscosity of the water is estimated to be about 0.4 centipoise. Okay, so the dimensionless radius is the radius of the aquifer divided by the radius of the oil zone. So what we're talking about here is there's a 5 times multiple. So in other words, the radius of the aquifer is estimated to be about 5 times that of the oil zone. And we're not dealing with a full 360 degree contact where the aquifer is impinging on the oil zone. In this case, it's felt to be significantly less than that, maybe around 80 degrees or so. These parameters over here are specific to bottom water drives or linear drives. In this case, these values that we have entered here are not being used at all by the program. To continue on down here, this is the historical information that we were looking at in the previous charts. Here is the dates. Again, they're on 50-day intervals. As you can see by the cumulative days are going up by 50 days per step. And the historical reservoir pressures that were measured for the field. Cumulative oil volumes, cumulative gas volumes. There's no gas injection in this case. We do have some water production, and there's no cumulative water injection. Okay, so that's it. Really, we have all the needed data in there, and we may find ourselves needing to change some of these parameters in order to get a nice straight line on our material balance. So let's roll off to the right here. Now, what I think we'll do is I'm just going to come in here, and I'm just going to put a temporary split here. So we can see that the data on the left-hand side and the data on the right-hand side also. And we'll move off to the right here shortly, but before we get on, I wanted to just refresh your memory that this is the equation of the material balance equation here that we're going to be dealing with. So N is the original oil in place, and it's a function of many, many parameters. And what we do is we group a number of these terms, and we therefore refine this equation to the one that we'll see below here, which is then used to be rearranged in the form of a straight line. So the previous general form of the equation then is rewritten in this form, and these various new terms, the F, the EO, the EG, so on and so forth, are then equivalent to these terms here that you'll see on the right. Okay. So in this case, let me just step out a little bit here. So in this case, where we're dealing with a reservoir that's undersaturated, but with a with an aquifer, what we're going to do is I'm just going to hide a number of these columns here. And just give me a sec here. I'll just get rid of some of this other information that really pertain to other scenarios where we do have gas caps, etc. So this situation that we're dealing with here, and I'll just hide this one over here. This one that I'm hiding right now pertains to a reservoir with a water drive and a gas cap. In this case, we do not have a gas cap. So we're just going to get rid of that. So here it is here. And so before we look at the analysis, I'm just going to zoom in and continuation with the discussion on the material balance equation. So this is the same equation that we were looking at earlier. In this particular case, M is 0 because we're well above the bubble point. There is no gas cap, so we're going to strike that out. And the cumulative water influx, which is W sub E, can really be written as a aquifer constant B times the superposition summation of the change in the reservoir pressure times the dimensionless water influx. So that term can then be written with that, rewritten in that form. And then so therefore we end up with this equation down here. Now it's this equation that we're going to split. Some parts of the equation will go on the left-hand side of the equal sign. Other parts of the equation will go on the right-hand side. We're going to plot, in this case, in the form of a straight line, the parameters on the left-hand side on our y-axis, and we're going to plot the parameters which are boxed in red on the x-axis. And this will leave the N, which is the original oil in place, to be the intercept, which is that point right there, which hits that y-axis when x is 0. And the slope of that line will be that aquifer constant B that we were talking about earlier. Now we have the ability to, well, I'll talk about that in a second. Let's take a look at the data. So here is the plot that we're going to look at, and you can see I've already been tinkering with this thing, so I've had this thing set up. It looks quite good. It's the data is going through a nice straight line. But I'll show you, I'll walk you through what I typically like to do. I'm just going to set this up to be, say, 5 times 10 to the 7th. And that's what that's going to do, is it's going to move, let's go 1.5. Okay. So that's going to move that line up a little bit. So what that basically does is the slope of that line is that constant B, the aquifer constant B that we were talking about. And what I typically do is I'll come up here and I'll pick a line and I'll lay it in here. I'll lay it over top of that. I'll then go right mouse click and I'm just going to set it up and create it so that it's a red line. Do that again. There we go. So now we've put in a line that is equivalent to that same slope. And what we can do is then we can just drag that line down and just see how well it matches the data that we have. And really that's a pretty good match. And so to continue on with the way this analysis goes is we would then read off that point there. And to me, it looks like it's maybe around 35 million barrels of original oil in place. This is 5 times 10 to the 7, and this would be about 3.5 times 10 to the 7, or 35 times 10 to the 6th, 35 million barrels of original oil in place. And the reason why I'd put a split in here is because it allows us to just sort of see how some of these other terms might change. For example, let's go with a 360 degree aquifer. It's encroaching on the reservoir 360 degrees. How much does that change? Well, quite a bit. You can see that now that aquifer constant that is calculated, it's a function of that aquifer contact angle, is now nowhere near the same slope of the data point. So clearly that number is too large. So again, if we put it back to, what was it, 85? It was 80 degrees. Then again, it comes up pretty good. We can also change the permeability. So I've got it set up right now at 10.5 millidarcies, but maybe we thought initially that it was 15. Well, again, it's if I were to take that, so we're a little bit off there. That slope is a little bit off, and so well, not only that, but that would be the correct line. And if we were to pull that up, then there it is. The slope is quite a bit off. So that tells us again that a permeability of 10 millidarcies with those other parameters in place just doesn't seem reasonable. So I'm going to put that back to 10.5. I'll just do this one more time. So if I set that up like that and get that guy lined up, then that comes down, and that again looks pretty good. So I'm saying it's around 35 million barrels approximately of original oil in place. Again, you can see how sensitive it is to some of these parameters. All right, let's go on then, and let's talk about the next step in the process, which is the history matching component. Here is the history matching tab, and you can see right now I've got things set up so that I've got 35 million barrels of original oil in place. I've got everything else set up accordingly, the same 25% porosity, 19% porosity, 25% water saturation. I've got the 10.5 millidarcy permeability. I've got the 80 degree angle, and we've got the same dimensionless aquifer size of 5 in there. So as a first pass, of course, we don't know what the pressures are to be, but I had earlier run this thing, and again, the way you'd run it is you just sort of seed some numbers down here, and you hit Control S, and then once you hit Control S, then it sort of iterates on a line by line basis. It'll then pick the proper pressures such that this calculated error then becomes very close to 0. So the proper answer are these ones here, and again, these were derived earlier before I started the video, so you can see the calculated errors are very close to 0. So that indicates that we're from the material balance equation is supporting the fact that these are good estimates of the reservoir pressure. And once we do that, then we can come way to the far right here, and we can see this. Well, actually, before we go on, this is a quick summary of what we're dealing with. Then this is telling us that the initial pore volume and the initial hydrocarbon pore volume are these values. Again, the original oil in place is 35 million barrels. There is no gas cap, and there is 14 BCF of solution gas in place. And the initial amount of connate water within the reservoir is about 13 million barrels of reservoir volume. And so to continue on, Now that we have everything calculated, we can just roll to the right here of the spreadsheet, and we can see the results in graphical form. And here they are. So this particular plot right here shows the same production data that we had initially seen. So the initial, or the field oil production of 6,000 or 7,000 barrels a day occurring for a period of time. The water production ramping up over time up to about 1,000 barrels a day. You've got your shut-in period here, and then you can proceed with a bit more oil production and water production. Again, the GORs were fairly constant the entire time. The thing that we have in addition to that original production data set that we had seen is we now have an estimate of the aquifer influx volumes, the actual rates that the aquifer is contributing into the oil reservoir. And these are shown here. They're of the same order of the amount of oil production that we're seeing. In some cases, slightly higher. In other cases, slightly lower. Keep in mind, though, that these water volumes, influx volumes, are at reservoir conditions, so they're in reservoir barrels, whereas obviously the oil production that we're seeing here is in stock tank barrels. But the thing that's interesting is that we note that even during the shut-in period, we are still seeing water influx coming into the reservoir. And this is the reason why we're seeing, if we look on this plot down here, those pressures rising throughout that shut-in period. Okay, so this is one of the things that comes from the analysis, is that we're seeing continued water influx, and we're seeing that amount of water influx is allowing the pressures to rise to that extent. Here, also on this plot down here, we're presenting the voidage replacement ratios. In this case, I'm calculating voidage replacement ratio not only as a function of the water injection rates and the gas injection rates, but also as a function of the water influx rates. So in this particular example, we are seeing voidage replacement ratios which are approaching that one value. And that's simply due to the fact that we do have these water influx rates that are occurring. By the way, these plots over on this, on the right-hand side here, is the same data, but it's just presented relative to cumulative oil volumes rather than time itself. If we go below down here, we can see a fluid saturation presentation, and it's relative to time also. And we can see that this shows the change in the fluid saturations within the reservoir over time. Initially, we're dealing with around 25% water saturation within the reservoir, and the remainder is filled with oil. We're above the bubble point in this case, so we do not have a gas cap initially, nor at any time do we have a gas cap for this period that we're analyzing. The pressures all remain above the bubble point pressure, and that is resulting in the gas saturations being zero throughout the entire time. And finally, this plot down here is a presentation of the drive indices and reservoir pressure over time. First of all, here is the reservoir pressures that we've measured as shown on the right-hand axis. The drive indices, as shown on the left-hand axis, are also shown. There's really only two drive indices that are having positive values. First of all, we have the water drive index in green here, which is some pretty significant numbers. We're as high as 90% at times with the water drive index, which is an indication of a good strong aquifer. And the remainder is made up of the expansion drive index, the expansion drive indice is due to the rock and liquid expansion within the reservoir. So you can see a portion of this oil is being driven towards the wellbores due to the expansion of the rock and the liquid, but largely the oil is being driven towards the wellbores. The pressure is being maintained to this level due to the fact that we do have that aquifer in place, and is the primary mechanism by which this pressure is being supported. And finally, I wanted to walk you through one last example. This particular example also includes an aquifer, but in this case, we're going to be dealing with a finite-sized linear aquifer. The reservoir pressure is going to be initially at the bubble point. So let me walk you through the production and reservoir pressure history for this particular pool before we go on to the analysis. This is the production history, and you can see that initially the reservoir produced 1,500 barrels a day of oil and did so for quite some period of time before eventually dropping off and declining due to the pressures falling in the reservoir. The GORs were initially around 600 standard cubic feet per barrel and stayed at that level for a short period of time and then rose as the pressures continued to fall below the bubble point. The measured reservoir pressures are shown here. Nice, a smooth set of data that we're going to be dealing with, and you can see a number of pressure surveys were conducted throughout the life. So let's do the analysis now. So I'm going to just get rid of that. I'm going to pull up my material balance spreadsheet here. So this is the material balance spreadsheet, and in this particular case, I've got a lot of the parameters already set up in here. We're going to be dealing with PVT correlation here, which is why I have a 1 that I've placed into this cell, which is indicating again that we're going to be using PVT correlations. Here's the oil properties. We're modeling a 35-degree API oil with 595 solution GOR initially. 0.69 specific gravity gas, and 160 degrees reservoir temperature. And this is the result of that analysis. We're showing that the initial pressure is going to be 3,000 psi, and that is going to be the bubble point pressure, and our solution GORs will drop off as the pressure falls. The initial oil formation volume factor is going to be about 1.34, and it then will fall off as the pressure falls below that. The gas properties tab is shown here. We've got a very simple case where we've got no nitrogen, no carbon dioxide or H2S components, and it gives us the information as far as what the Z factors are as a function of pressure and the formation volume factors. And then finally the water properties are input here, and those are all used in the material balance analysis. In this particular tab, or in this particular cell in the material balance tab, I have included a 1, which is to say that we're going to be considering water influx in this case. We're right at the bubble point pressure, and in this particular example we have no gas cap, which is why I have M as 0. The initial average water saturation is 30% in the reservoir and an average porosity of 15%. We're simply going to be using the built-in correlations to determine what the rock compressibility is for the reservoir, and again the water compressibility is coming from correlations there. Now, as I was saying earlier, we're going to be modeling a linear aquifer, which is different than our previous example where we had an Edgewater drive. So in this case I've typed in 3 in this particular cell, which is to indicate that we have that linear aquifer situation. This reservoir has an estimated radius, if we were to consider it to be a circle, of about 8340 feet. And the aquifer thickness is 40 feet, and the estimated aquifer permeability is around 20 millidarcies. Okay, because we're dealing with that linear drive, these particular group of cells are not impacting the analysis in any way. And it's only this last one here, which is specific to the linear water drive, that we're going to be using. Now, in the case of the material balance tab, I would recommend only using the finite situation where we have a 2 in this cell. Now, it is possible to model an infinite acting reservoir, but in the case of the material balance tab, in order to make things more efficiently, more effectively with the analysis, I would recommend always having a 2 in here. And if we do want to be modeling an infinite acting reservoir, we just simply have to increase the length of the reservoir here. So in this case, we're modeling a 3,000 foot width reservoir, which has a length of 10,000 feet. Here's all your dates, your cumulative days, your reservoir pressures that we've measured over time, the cumulative oil volumes, gas volumes, etc. And what I'm going to do at this time is similar to what we had done before. I'm just going to roll over here. Let's see, where should I do this? And I'm just going to roll over here, and I'm going to insert a split at that point, and then I'm going to roll over to the right. We had talked earlier in this video about how the material balance was formulated in the form of a straight line for an aquifer, so I won't revisit that at all. And you can see that I have already been playing around with this particular model, which again is using a water drive with no gas cap. That's the situation that we're dealing with. And if we zoom in here, you can see that through some previous work, I've managed to come up with a set of parameters which results in a nice straight line here. And in this particular case, as you can see, first of all, if I take this red line that I've sort of drawn in here, simply drawn in here, and I move that up, that's very, very equivalent to that aquifer constant, the B value. So that's what we're using. That's what we've calculated with those input parameters. And if I drag that down, it matches very nicely the historical data. And in fact, it crosses it provides an intercept value of 30 million barrels of original oil in place. So that's a good estimate for what the original oil in place is for this particular reservoir. Now, the reason why I put the split in here is I just sort of wanted to show you how sensitive things are when I tinker with some of these numbers. If I were to come in here and say that, no, I don't think that the length of this aquifer is only 10,000 feet long, I think it's 20,000 feet long, which will provide a period of time which is going to be infinite acting longer than what the 10,000 foot reservoir would give us. So if I hit enter there, what you see is a curling over of the data points. And again, the whole concept with this material balance procedure is to try to come up with a straight line. Clearly this isn't. And in this particular case, 20,000 feet is too long. Just for the heck of it, let's try 40,000 feet. and it becomes actually arguably even worse. So if we were to go the other way, and let's say 15,000 feet, then it should start straightening out on us a little bit more. It is, but we still have a few of these points that are not consistent with the other points. So really what I had done in order to come up with the 10,000 is I just kept playing with it, and there you go. So the 10,000 seems to match the data very well, again supporting the 30 million barrel of original oil in place. Okay, what we could do, and maybe show you a little bit of this over here. What if we were to say that no, we don't believe that this is a linear aquifer at all. It's maybe an Edgewater drive. Well, in this particular case, this data, I mean, it's tough to see. I could rescale things. It does look fairly, like it arguably could be straight, but the slope of that line is significantly off. So we could come in here and maybe play with the aquifer contact angle. Maybe it's 180, which will flatten out that line, but still we're significantly less. Or maybe the dimensionless radius of that aquifer is less than that. Let's maybe try 1.5 or something like that. Really, I mean, I think we could play around with it a little bit more, but it's hard to really come up with a match. The only thing that I'm really able to come up with a decent, and in fact a very good match, is by modeling this thing as a linear aquifer with a finite condition and a 3,000 foot width of the aquifer and a 10,000 foot length. Okay. So the next step would be then to continue on to the history matching component. And as I recall, I think I've got things set up reasonably well here. I've got the same parameters. There's my 30 million barrels that I've placed into the history matching, which I've taken from my original material balance analysis. And I'm going to be modeling a linear aquifer with these parameters, the thickness and permeability of the reservoir. And I also have that finite linear aquifer here, 3,000 feet wide, 10,000 feet long. So we would fully expect to see a nice match on the data. Okay. So again, what I would do here, in this case, in order to generate those numbers, I would, and I'm not going to do this. I've already got the numbers. I've already done the work, so I'm just going to explain to you how I did it. Typically, what I'll do is I'll put in a number here that's slightly less than the initial pressure, and I'll just sort of copy it down to all the cells where we need to calculate, and then I'll just simply hit Control S, and that will run a macro that will iterate on a line-by-line basis and determine what those values are. Now, as I was saying, I've already done that work, so here is the result of doing that analysis. And you can see that the pressures appear quite valid because the calculated error is 0 in every case all the way down. Okay, so let's take a look over to the right here. Again, here's the results of what we're dealing with here. Here's the initial pore volumes, hydrocarbon pore volumes that are reported, the original oil in place. Again, no initial gas cap, but just a solution gas volume of about 17.8 BCF. And so now that we have everything calculated, we can just proceed off to the right and take a look at some of the resulting graphs. Okay, so here are the results here. This first graph is a plot of the production rates and GORs that we had seen initially. Again, there's our oil production rate of 1,500 barrels a day, flat for a period of time before starting to decline down. The GORs were initially around 600 cubic feet per barrel and then began to rise slowly over time as we continue to fall further below the bubble point. This is the same data that is shown on the over here, but it's shown relative to cumulative oil production rather than time. The thing that we have in addition to the produced volumes are estimates of the aquifer influx rates, and that is shown here. Now, this is a linear aquifer that's not particularly of high quality. So consequently, the amount of aquifer influx that we're seeing into the reservoir is in the order of 100 barrels a day, and then declining down as pressures diminish. Uh, Contrast that with the 1,500 barrels a day of oil production, and we are seeing some support, pressure support from the aquifer, but not a huge amount. It's not a great quality aquifer in this case. So if we were to look down below, we can see estimates of the reservoir pressure. And so the blue data points are the resulting values that comes from our history matching analysis. And the open red circles are the actual measured pressure data that we had input into the material balance tab. And you can see, obviously, there's a very, very good match between the two, which is indicating a pretty valid analysis. We also have the voidage replacement ratios, which are shown here, and they're not very high at all. They're less than 10%. Those voidage replacement ratios that we're reading, if we were injecting water, if we were injecting gas, the voidage replacement ratio would change accordingly. But in this case, all that's happening from that perspective is water influx, as we can see again in these points up here. And it's not a huge amount of water influx, so therefore our voidage replacement ratios are not very large themselves. They are positive. There is some support that's occurring due to that, but not a large amount. I suppose one of the main points is that the pressure is dropping. We're clearly seeing some dropping pressures in the reservoir, and that initial pressure was the bubble point pressure. So consequently, when we scroll down to look at this graph down here, this is a plot of fluid saturation over time. We're seeing that in the red, we're seeing an increase in free gas saturation as time proceeds. And that's simply due to the fact that our pressures continue to fall further and further below the bubble point, allowing those gas saturations to increase. The aquifer, again, is not a very strong aquifer, so our water saturation is relatively constant, still rising slightly, I'm sure, in the reservoir, but not to a large extent. And it's really, the saturation changes is really the oil saturation and the gas saturation, the free gas saturation, that is, which are the main changes within the reservoir. As we scroll down to look at the drive indices that we're calculating, first of all, again, here is our pressure history as shown on the right-hand axis. In the black up here is our depletion drive index, which is really a result of the solution gas drive mechanism, and that's representative of 90 or so % of the total drive indice within the reservoir. The remainder is made up of two things: a little bit of expansion drive index, which is due to the expansion of the rock and the liquid within the reservoir, and finally the water drive index. Again, we've already mentioned that it's not a big aquifer, so therefore we're not seeing a huge drive indice from the water drive component, but we are seeing some positive values. Again, the main drive mechanism for this particular reservoir is that depletion drive index.